book and you're able to read some of the notes on your own from the class book. Today, I just want to do one very critical thing. We are embarking on the ladder logic programming, and we are now going into it in depth. And so we are not going to be talking about a lot of theory. We are going to be actually looking at real circuits and real diagrams, and then looking at other problems that we can solve using PLC. So we are now into the real programming bit of the course. So just before we go there, I would like us to do something on the rules, because I need to just explain a few things. I told you there are about 7 rules, not 9, 7 rules that have, there are several rules, but the key ones are about 7. Those are really basic. They're really important. So I will go into that. Then we start looking at some of the problems that exist in the real world. So let me just share my screen, sorry, and then provide you. Oh, sorry, my. Sorry about this. This has, I think my stuff has locked. So I think. Okay. Please just confirm that you can see my screen, please.
Yes.
All right. Thank you. Okay. Thank you. So I will just begin with the programming rules. I just want to mention a few things here in passing, so that I reiterate a few points that are very important even as we carry on with ladder logic programming. Now, we have several manufacturers provide their rules, but that just depends on the fact that they have a slightly varying PLC programs. But the key rules that I'm going to talk about today are sort of, they cut across all these manufacturers. It's the same thing. They're general rules. That's why we call them basic, because you can't do away with them. You can't wish them away. So they're just the basic rules that are very important when anyone is considering drawing a proper ladder diagram and then implementing it. Now, the first rule is the one that we have been talking about a lot, where we say that a scan cycle begins from the left to right, top to bottom. So the PLC scans from left to right. Sorry about that. Scans from, okay, let me just say scans the ladder diagram. From this rule helps you a lot even when you are analyzing PLC diagrams, because in certain cases you are given certain ladder diagrams and you're expected to figure out what it does, also from top to bottom. So this rule is critical. We have to remember that. The other rule that we also have to remember is on the scan cycle itself. And we say that it's a repetitive process. It's a cyclic process. So the scan is cyclic. And usually, I told you, each scan cycle, the time it takes to complete one scan, that's the scan cycle, is just a few milliseconds. But it doesn't mean it stops. It repeats indefinitely until you actually execute the whole program and maybe stop the PLC from running. But the PLC, once it is, when you actually run it, it will just be like repeating itself through and through. After every few milliseconds, it repeats itself. So it's important that you also remember that, okay? So the scan time is in milliseconds. That's another important thing to remember. Now, you can actually see that the information that I have provided here doesn't really help you with drawing the ladder diagram per se, but with understanding how the ladder diagram operates. Now, the other one that again helps you to understand ladder diagrams, as we are going to start studying them soon, you will notice, and I think I mentioned this in the previous class, the other rule that we have to remember is that every time a scan cycle happens, we do not update the output. We evaluate and note, sort of, we sort of note the state of the output in every scan cycle, but it will not be updated until the very last moment when all the scans have been run, and then at the end, that is when the outputs are updated. And I explained the reason for that is if you're having a PLC that, for example, operates a motor, you do not want to be updating the output every time before the scan cycle is complete. Remember, I said if you have rungs, I'm not drawing anything in between. So if you have rungs and you're beginning from left to, and you're going like that. So, and then you know, because it's left to right, top to bottom, like that. It is important to remember that when the output is somewhere here, this is not going to be updated immediately. It will be evaluated and the state will be known. If you have another output here, it will be evaluated and the state will be known. If you have another output down there, it will be evaluated and the state is known until the scan cycle is complete. Once the scan cycle is complete, that's when the output status are updated. And updated simply means the value that was existing there is changed, is written over. Because remember, the scan cycle was read, execute, and update in that order. And we said it is cyclic. So we have to remember that the read and execution, because we are executing logic expressions, these ones can happen in every rung. So you read the rung and you execute the expression or the instruction that is there. Then you note the status of the output, but it is not updated immediately. It is just evaluated so that we know that that rung should have that state. Then the output in that rung should have a particular state. We move on because the scan cycle is not complete. Again, we evaluate the next expression or the instruction that is given in the next rung. Then we note the output that is deserving in that rung. And then we evaluate again. So once we finish, once we get to the last one and all the instructions have been executed, that is when the status of the outputs are now updated. So now they are written over so that there is an actual state there. Because at the end, that is when that output is actuated to operate a field device. So this update is usually done at the end of the last at the end of the scan cycle, while read and execute happens in every rung, because every rung has a set of instructions that must be executed. So each rung will have a read and execute instruction, but the update is not done in every rung. The update is done at the end of the scan cycle, where you now update all the outputs. I had to take time on that because it's very, very important that we remember that the update is done at the end. Okay, so it's a rule that we must understand, okay? That the states of the output, let me just say the output states are evaluated as the program scans through the rungs, through the rungs. But they are only updated at the end of each scan. And because, like I said, okay, and because there are so many ranks with outputs, for example, okay, so many ranks with outputs, for example, when they're updated, they're all updated simultaneously. Okay, so this is updated, then that, then finally that. So in fact, simultaneously. So please note that the state of the inputs can always change in each rung. The state of the inputs can always change in each rung, even before the scan cycle is complete. But the state of the output is updated only at the end of the scan cycle, when now we already, or the processor has figured out exactly what the instructions were and they have been executed, then now they can update the outputs only at the end. Okay. Okay. Rule number 4 is a basic rule, which again, this helps you while you are actually drawing a ladder diagram. If I see your ladder diagram and I see that there is no input, then that is not a ladder diagram. So a ladder diagram must have at least one input. And now you know what I mean by the input. It means we're talking about either a normally open contact or a normally closed contact. Because these inputs, remember we said they give you the instructions, the logic instructions, from where we get the logic expression. Remember, if you remember correctly, you have something like that. So the input side here, the input side is where we get the logic instructions. Because you remember we had if A and B, then you get your output. So the entire rung is a logic expression, but the input side is giving you a logic instruction. I hope that is clear. So the input gives you the logic instruction, but the entire rung here, when done, written out, you get the logic expression. So each rung provides a logic expression, but the input side gives you the logic instruction. So again, I hope that is clear. The rule, therefore, is that every ladder diagram must have at least one input. Must have at least one input. And that input, that is at the start of each rung, because you might find that the next rung does not require an input. There's an output device. But at the start, when you're starting, there must be some input device. The same way, rule number 5, same way, rule number, I think you have these rules in your notes already, but there must be at least one output at the end of each rung. There must be at least one output at the end of each rung. So if I find that your ladder diagram is like this, for example, then that is not a ladder diagram, because you have provided an instruction, but that instruction is not translated into an expression because there's no output. So every rung must have, at the end, there's always an output. And remember, it is very significant because the output module is always given the same address as the output coil. So the output module will not be able to interface with the field device if there's no output coil. So that's why every rung must have an output, because otherwise, how will you be able to connect to the field device? Because the output module needs to connect the field device or interface the field device with the output coil. So that's why it's important. Okay, rule number 6 is that each rung in the ladder diagram represents a logic operation. Okay, so each rung, this one I have already mentioned, each rung represents a logic expression or operation. Okay, I told you, I put it up here, that the input side gives you the logic instruction, but each rung, in a complete rung, provides you with the logic operation. So therefore, that's why when we are commenting, that's why I told you, when you're commenting on your ladder diagram, you provide comments for each rung, because each rung stands for its own logic operation or its own logic expression. So you could be writing, so if you had a ladder diagram with 4 rungs, then at the end, you'll provide comment 1, comment 2, comment 3, comment 4. Then you're done, because comment 1 will tell me what rung 1 is doing, comment 2, what the logic expression for rung 2 is, comment 3, what the logic expression for rung 3 is, and comment 4 is what the logic expression for rung 4 is. Okay, so that's why each rung must have, it's basically a logic expression. So it must make sense on its own. You cannot have a hanging rung where the logic expression doesn't make sense or is incomplete. So each rung must have sort of like a complete logic expression. All right. The last, but not least, very, very last, but not least rule is also something that we have mentioned before. But you might miss it. Very important. And the rule is, you might have an input or an output that is used more than once. Meaning, because we are trying to say, you cannot have, if for example, let me just give another example here. Let me put anomaly. So, for example, you have a ladder diagram. I've just drawn one rung. So let's say this is A, B, and this is Y. Sometimes you might need the state of this output to be replicated or to be used more than once. So we are going to do one example, which we're about to start, to illustrate this point. When we need the state of this output, but we need to use the state as an instruction or part of the instruction, then we are allowed to take the output and make it an input. I'll repeat that. Sometimes we need the logic state of the output to be part of the input for certain applications, and you'll see some of them. When you do that, then you need to replicate that state of the output into the input. But when you do that, the rule is you cannot draw the same output as an input, because we had said all inputs are to the right of the ladder diagram, all inputs are to the left, all outputs are to the right. All outputs are always on the right side, and all inputs are always on the left side. So now remember, let's say there's a state here that I need. I need this state 1 to be used as part of the input, as part of the instruction, because it maybe in the first rung, I needed to achieve that logic 1, but I need to use that logic 1 as part of the instructions for the next rung. So because the rule does not allow me to use a coil or an output as an input, I'll have to draw or replace that input. I'll have to replace that input with just the normally open contact. But I have to name it or label it exactly the same way I label the output. So if the output has an address, so let's say it's called output 0.1. Okay, let me put Q so that I differentiate it. So let's say the address for this output is Q 0.1, but I need to use the logic state there as part of the next instruction. Then I use a normally open contact. So notice I have replaced the output coil with a normally open contact, which is an input, but I have to give them the same address. So this, I'll call this Q 0.1, so that the processor will know the state of the output, right? But then it will understand that I'm supposed to pick the state of the output address and use it as an input. So notice that the address for this output is exactly the same as the address for the next input. However, the devices are still different. One is a coil, one is a normally open contact. So the contact and the coil are used strictly. Coils are for outputs. Contacts are for inputs. And those contacts appear on the left side of the rung. The coils appear on the right side. But if I want to borrow the state of the output and make it an input, I'll just use the contact, but I'll use the same address of the output to be used in the input. We'll do an example with this so that we see that. Over and above that, certain times you have your ladder diagram can be so extensive that sometimes I want to have reached, let's say this is 1, 2, 3, 4, 5. So maybe the logic expression that I obtained in rung 1, I need it in rung 5. So if I need the exact same logic expression that I had in rung 1, I need it in rung 5, I don't have to repeat the exact, I don't have to write new or copy like new contacts and coils. All I have to do is I copy the address. So it's like you tell the processor that when you come to rung 5, where you want to now execute instruction number 5, just go back to the memory address of what was there in rung 1 and repeat it. Okay? So you use the same tag name and address so that you borrow the inputs and also borrow the outputs. So every time I want to use an output twice, I simply use the same memory address system so that we avoid replication. Because if you write a new output, but it is still performing the same thing, there are redundancies. So we don't want that. What we want to do, we are optimizing our ladder diagram. So if I want to borrow an input, for example, I want to use the input that I used here is the same input I want to use here. I simply, the address that I gave here, so let's say it was input 0.1, is the same address that I give here, 0.1. So that the logic state of the first input rung is also going to be the logic state of the second input or the third input in the third rung. Okay? So that is what we do. That whenever you want to borrow an output or the state of an output or the state of an input, you simply use the same address and the same tag of that output or that input in the second rung or in the third rung or in the last rung, so that the processor knows that you simply need the state of the previous contacts. That's very important. Again, it will be clearer when we do examples. So, ladies and gentlemen, these are the rules. These are the rules. So, I didn't put it in words. So I could say that to use an input or output expression more than once, in the ladder diagram, we simply use the same tag, tag name and address. We use the same tag name and address. Okay, so whenever an address is used more than once, we know we are replicating the expression for that rung or for that contact or for that coil. That is what we do. All right, so I just needed to elaborate on those rules. You have them in your notes, but I needed to elaborate on them because they are very important. So by now, we have also seen that it is critical for us to have and I think we did this when we drew a typical ladder diagram and we indicated some of the must-haves in that ladder diagram. So we know this is rail 1, we know this is rail 2, okay? So we know that this is a normally open contact. So we have to give it an address. So sometimes you can call this A, B, for example, and Y, but those are not addresses. There is a name. So we can call it, the name is A, or the name is B, or the name is Y. Or alternatively, you can say the name is normally open, the name is normally closed. This can even be normally closed. Okay? And the name here could just be an output. Okay? An output coil. But you have to provide an address. So the address here could be input 0.1. This is input 0.2. Okay? Input, so it should be I. This could be maybe output 0.1 or Q 0.1, whatever it is, whichever address you provide. And then usually it's also important to provide comments. We had agreed what comments are and why it's important. So the address, you can see, consists of a data type, meaning there is some integer that is being used to be part of the address. So it's not just an input, but the address is 0.1, 0.2, 0. And so on and so forth. So those are very critical parts. And again, remember, when you look at the ladder diagrams that I've given that are provided for in the book and also in your notes, you will see that those ladder diagrams usually provide all the information that is needed so that we also practice the same courtesy of making sure that we label our ladder diagrams properly. All right, now I want to give one example before we end the class, but just to mention that addressing is very important. It's providing the address. So I have provided notes on how you can address, because different manufacturers have their different addressing systems. So you can have a look at what exists in Siemens environment, what exists in the Rockwell environment. Rockwell is the Allen Bradley PLC. So you can compare. It's just using different symbols, but the method of addressing is the same. So again, those are provided for in your notes and you can read them because it's difficult for me to cover everything in class. The other part is the software element, because we are doing programming. So again, I encourage you, because these things are available, you can always download PLC software and use it to simulate some of the PLC problems that you encounter. And you can do it at home. You don't have to go to the lab, because this is just you just need to download the cymatic. For Siemens, you have the cymatic step 7. And it's available. I think I also shared it in my Google Drive, so you can always check. I think I provided a link where you can download it. But I'm sure you guys are smart enough to get some of these programs online and download them. And then also make sure you download the data sheet. And then you can always try and run a few programs on your own at home and check, because usually you have to draw a ladder diagram to represent certain, you're trying to implement a certain thing in PLC, so you have to draw your ladder diagram. Once you have completed drawing your ladder diagram, you need to compile the program, just like you do with the other text-based programs. So you have to compile, because when you compile, it simply checks for syntax, it checks for errors, it commits memory for the program. So compiling is important. And usually during compilation, that's where if there are any issues, then the software will indicate to you where the problems are, and then you can correct them. So you can always fix the problems that exist during compiling. So once you have completed your compilation and you've made sure that you have corrected all the errors that may or may not occur, then now you can run the PLC. So once you run, just like we are running the normal, just like when you use MATLAB, you have to run the code or the program. So again here, once you have completed your syntax corrections, then you can actually run the program and see what happens, okay? And like I told you, the ladder diagram provides the best environment for debugging, because in a C, for example, you will really have to go through lines of code to check, where did I make that mistake? What did I omit and stuff? But for PLCs, usually they even direct you exactly to where the problem is. So it's a very, very easy software to operate, because even debugging your ladder logic program is easy. It will quickly point out where the mistakes are, and you can always correct them. Okay, so the lab uses, like you have known already, the Cymatic Step 7 software. So you can always, even if you don't have, you can speak to Aweru and from the computer lab, and then he can provide you with that software and then install it in your machine and try to do some of these simulations. They're very, very important. They'll give you a better idea of what happens. So now allow me to share with you, because I think I needed to indicate this in your notes. So I'm going to share this with you so that we look at it. Okay, now I missed it. Let me see if it will load. Okay. Okay. Let me just set up something here, ladies and gentlemen. We do one last example, and then I don't have an Acrobat reader yet, so this thing sometimes usually just makes my life difficult, but I'll manage. So I'll stop sharing, and just give me a minute, please, so that I find the file that I'm looking for. And then I share with you in a minute. So what I want to do is simply show you one diagram. I think you can always even open it yourself from your notes. But for me, I know I have it. Just want to open it now. All right. Okay. So I think now I can share. I want to explain this, and then we are done. I think you have the notes, so I shouldn't be bothered. I just wanted to give you a practical example. That's why I put it here in your notes, so that we can relate. We can relate with real world stuff. Okay, so ladies and gentlemen, if you see, this is an electrical schematic. All engineers know that you have to draw an electrical diagram or an electrical schematic of whatever it is you want to do. The beauty with this is at least now we can illustrate some of these things with some pictures that show you what exactly they are when you buy them as a module in the market. So now you can see this is just a very simple motor starter control. Like it helps you start a motor and stop a motor and stuff like that. it doesn't change speed or anything. It's just for starting and stopping a motor. But this is for manual operation. So you can see the electrical schematic, of course, has a circuit breaker for electrical protection that you know by now. Any engineer knows that any electrical wiring system must have a protection system. So here you can have the circuit breaker to protect you from or to connect you to the mains. That is the main supply of the electricity. That's what we have here. And okay, I needed to see if I can use certain, I can mark this so that you can see. Ladies and gentlemen, I'm sorry. I needed to see how I can mark this properly. So allow me again to just, because I don't want to bother you with my scrolling and looking for my files. I want to open this in the environment that allows me to show you exactly what happens, and I can draw. So I need to import the file. So just give me a minute. Again, even as you open your own, I just need a minute to import this file so that it's also used in our study. Okay, I'm just trying to get it from sometimes, you know, it's interesting to use this technology, but they help a lot. So I want to import. What I wanted to do basically is just to show you practically how some of these programs are very, very critical. Because we can need them in the industry. Now my file is lost. And I have to search for it. The title of our notes, I think it's ladder logic. Okay. Okay. So I've given you guys a smoking break for those who are smoking. As I'm looking for my file setting up, it's just going to take me a minute, so don't worry. Got it. Thank you. So let me share again, because I found what I needed. So those who went for the smoking break should come back on a light note. All right, so here we are. Now I'm able to edit my document. So I just wanted to show you certain operations that are critical. I'll expand this further. So now the essence here was to show you that every electrical installation must have a schematic. You have to draw a diagram that represents what you're doing so that somebody else, any other engineer, can come later and follow through and see exactly what is happening. So we can see, like in our case here, we have the circuit breaker element, where it's simply to connect us to the mains of the electricity supply. And then you've got the contactor for the motor. So this is what comes into contact with the motor. And of course, the contactor comes with an overload relay, just in case there's too much current to protect the windings of the motor, because otherwise you blow up the motor and then you'll have to do some rewinding. And usually winding is a serious, it's a costly affair. So, and of course, you have the start and stop push button to allow you to be able to start the motor and stop it at your convenience. But that is not my agenda here. My agenda here is to spend the next 10 minutes to simply show you how this is implemented in a PLC environment and see whether the rules that we were talking about, the basic rules, the 7 basic rules are adhered to while we are trying to represent a motor starter control system using a PLC, okay? So now, usually whenever, because what happens in an exam environment, for example, is I would probably give you a schematic like this and then ask you to draw a ladder diagram that represents this that implements this in a PLC program. So what you will have to do, and that is why I had to show you the schematic, because remember, the schematic is what you transition from when you're going to the PLC itself. So the idea is, the reason why the schematic is provided is for you to be able to identify the key things that you need. So you know that in your ladder diagram, you can identify input devices and identify output devices. So for example, the input field devices here should be easy to identify from the schematic itself. We had done this previously, and we said that these input devices could be like push buttons. So in this case, we have a stop push button. So the stop push button is going to be an input field device, meaning we'll need either a normally open contact or a normally closed contact to represent this button. We also have the start push button. Again, we'll decide which one, whether we need a normally open contact or we need a normally closed contact. We will see why we have to pick a certain contact. So these are, you can see, those are the only input field devices we have. However, if you check clearly, you can see even from the schematic that there's a symbol that is looking familiar. That symbol is a normally closed contact, and it's for the overload relay. It's for this device here. It's for the overload relay, the one that actually protects the motor from currents and stuff like the excess currents, and will probably protects the windings of the motor. So because it is a relay system, we need to represent this in the PLC, because the PLC must incorporate all the protection mechanisms of your field devices. So we've identified the stop push button, we've identified the button, and we also need the overload relay. So the overload, but for this case, we are going to assign it. Remember, each of these need to be assigned an address, and each of these is going to have logic equivalent. That's why we are putting it here. But we know that the overload is usually a device that's inbuilt. That's why you see it comes already with the contactor. It's inbuilt into the system to protect. It's not a device that you decide when to go and switch on and switch off. Unlike the start and stop push button, where you are the one to physically switch on and off, the overload relay switch is never static of the entire system. But we have to consider it when we are doing our PLC diagram, because it is part of the internal protection of the field device that will be operating. So the overload relay is part of the input field devices, but it is not one that we are actually, or we also have to take into consideration that. I hope that is clear. So once you have, I've given you the steps of the best way to draw a ladder diagram given an electrical schematic. So now we have identified the input field. It's a simple one. So quickly I'll move on to the output field devices. So how about the output field devices that we can see? Here, I can only see one. It's this guy here. So it's a motor, because it's the device that we are actually operating. So it's a motor. And so this motor, definitely to start, they will need to have a starter. So the starter is here. You can see the starter is the one that's actually now connected to the output, because it's like it tells the motor to start. So the starter point is there. So we have identified the output device, which is what kind of PLC input are we using? So now this is the field device, but for PLC, so input PLC device. So input PLC. What are we going to use? We need a symbol or a contact for stop push button. And I told you the stop push button is represented normally because stop is when something was running and then you have to stop it. So it means something was already allowing logic to pass through, and then now you need to deactivate it or need to stop that. So usually we use, for the stop push button, we use a normally closed contact, because it's a normally closed contact in its normal state allows logic to pass through. So a stop push button is best represented using a normally closed contact of the PLC part. Remember, the input devices are physical devices. The PLC is the software part. So the start push button, of course, is the opposite. So this is usually best represented using a normally open contact. And of course, the overload relay, you can see that even the schematic has the same thing. The overload relay is already represented there using a normally closed contact. Because remember, the overload relay allows the current, or in this case, allows logic to pass through. Like, let me talk about the electrical part. It will allow current to pass through until it detects that the current is too high, and then it breaks the circuit so that the current doesn't pass through anymore, so that we protect the downstream equipment, which is the motor. So usually that's why it's always closed, so that it allows current to pass through. It's normally closed, but as soon as it detects an overcurrent, it opens, and then it protects the downstream equipment. So that's why I was saying that's why we now have a normally closed contact to represent the overload relay. Because remember, we include, though it's not a button, a physical button, but we have to include it in our PLC representation, because the PLC must also take care of all the protection mechanisms for your system. Okay, I have 10 minutes, so allow me to move on to quickly explain the diagrams that follow. That's exactly what I'm doing, and then we are done. So this is a ladder diagram that has been drawn. Again, it's very easy to follow, but now remember, the physical device is here. You can see it's a normally open contact for the start push button, a normally closed contact for the stop push button. Of course, the overload relay is inbuilt, so there's nothing we can do there. Now, notice the symbol. Notice the start push button. It's open. That's why it's a normally open contact. So to activate it, you need to push the switch, because we usually push a button in for it to make contact. Normally, the stop push button is already closed. You can see that. So that if you push it, you break the contact. Now, that is the field part. So this is the field device part. Okay? But now we've got the input points. Now, this input points is where we had our input module, that component for the PLC, the input module. Remember, we had drawn the architecture of the PLC. So this is where the input module falls in. Why? Because it's interfacing. You can see it has an address that is similar to the what? To the normally open contact. So it's interfacing the field device with the software or the PLC contact. So that here we have input 0.0 is the same as the first device, which is input 0.0 in the program. So the physical device is given an input point, which is the same address as the normally open contact. And I've explained that the reason for that is because the normally open contact here is a representation, a software representation of the contact here. So please remember that usually the normally open contact here will be probably 5 volts or 10 volts or whichever, but that is translated into a logic. So here it will be either logic 1 or logic 0. So remember, this is an electrical signal, but now here we are dealing with logic. So the input point simply converts your electrical signal into some logic. That is what I wanted to say. The same thing with the stop push button. The stop push button, we've said, is a normally closed contact because it's allowing current up until you press it, then it breaks the circuit. So we need to translate that to logic. To do that, we have to make it have the same address as a normally closed contact. So now you can see that in my diagram here, we have used a shaded contact to mean that now it's logic 1 up until you press the stop push button, then it will come back to logic 0. So as it is, it means that the state here, the state of this is logic 0, the state of this is logic 1, because that's why it's shaded. That's why I told you different PLCs will give you their different symbols and you'll interact with them. So because it's shaded, it is closed. So it's a normally closed contact because it's shaded. And then, so that means it's logic 1. So if you activate it, that means if you press the stop push button, then it opens. And therefore it will transition to logic 0. The overload relay for I0.2 is also normally closed. So you can already see it shaded to mean it's of logic 1. The one that's not shaded is I0.0 because it's open. It's open. Notice the output is also labeled Q0.0 because this is for schematic. Q0.0. And it's Q0.0. It's the only output that we have. But notice that it is given the same address. So here we have the output module for the PLC that interfaces the motor starter with the program, the CPU program for the output. So notice that this address Q0.0 is the same as this address here. So that we know that here, if you get a logic 1 at the output, that logic 1 would be translated into an electrical signal because the motor does not understand logic, but it would be translated into an electrical signal, which then would actuate the motor and the motor would start running. So remember, we are talking about having an electrical signal on one end. So this end is electrical, this end is electrical, but this part is simply software. So we have logic. So here it's based on logic, but here we have electrical signals. Okay, electrical signals. And the same thing here, we have electrical signals. Okay, so that's the essence of interfacing these PLCs in that order. So how does this operate? Because I have 4 minutes to explain how this operates. So now let's go to the next diagram and see how it operates. It's very simple. So now somebody presses the start push button. You can see there's a hand pressing the start push button. When that start push button has been pressed, it makes contact. Now the contact exists. You can see there's now a contact made. Once the contact is made, it therefore means that the input module needs to change the state of the address so that that electrical signal would now be translated as a logic 1. Remember, it was a logic 0. It was a normally open contact. So it was a logic 0. But now see, it is a logic 1 because now see it's shaded so that the state here is now logic 1. I0.1 and I0.2 are still logic 1 as they were. But now, forget about this lower part for a moment. Just forget about it for a moment. So you have a logic 1, you have a logic 1, you have a logic 1. And we agreed that this would mean if logic 1 and logic 1, we have another and logic 1, then so you have 1, 1, 1. So if you AND these inputs, if you AND This is what I mean. If you AND these inputs, then you get a logic 1. So here will be logic 1. That's why it's shaded. And as soon as it's logic 1, during a scan cycle, the whole processor will run through the entire rung. Once it's completed the rung, that is when it updates the output. Once all the rungs have been exhausted, in this case, we only have one rung. So once it's completed the rung, meaning the scan cycle has come to an end, then it updates the output to logic 1. The output module will take that logic 1, translate it to an electrical signal, which then helps to start the motor. But remember, it's because this guy here pressed. If this guy releases his hands, and this is the last thing I'm ending with, if this guy releases his hands, then this will go back to logic 0 and the motor would stop. So it will be something like trr, 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 which is not the normal way to operate a motor. We have to find a way in which this guy needs to press the normally open contact or the start push button. Then even when he leaves or he removes his hands, the motor would still run. So how do we ensure that? That is what is explained down here, and that's what we talked about previously. To ensure that this motor continues running even when his hand is out of the start push button. Because when you press this button, usually you press and then you release. You don't hold your hand there forever for the motor to run. You have to release, but even when you release, you expect the motor to continue running because you've pressed start, so you expect it to continue running. So the only way to circumvent that is simple. It means because you had pressed initially and turned the status of the output here to 1, we need this status of the output to remain 1, because remember, the output module is communicating with the output coil. So we need that status to remain 1 up until we press the stop push button. So because we need it to remain 1, the quickest way to do that is to bring that status to the input. And notice it's brought to the input as an OR, so that now you see this Q0.0, it's the same here as Q0.0, meaning this is an input device which will always have the same logic as the output. It's an input device that must always have the same logic as the output. So in our case here, the logic, as soon as the guy pressed the start button, this logic turned into 1. And as soon as this logic is updated by the PLC program as 1, then this logic now also becomes 1. So because this is logic 1, even if this guy releases his hands, then we know, because when he will release his hands, this will go back to logic 0. Because if you stop pressing the start button, it means the contact will break. And when the contact breaks, this goes back to logic 0. But because we already have a 1 here, we'll be having either 0 or 1. That's why I'm saying it's connected here in parallel, so that it is either 0 or 1. So that even if this is 0, we still have a path here. So we'll still be having 1, 1, 1. Because yes, the start button has been released, so this contact has gone to 0. But at least we still have the output that we had taken previously has been replicated in the input. So it is providing a path for us of logic. So it's still having logic 1, logic 1, logic 1. So this guy remains logic 1 and the motor keeps running. And because this is logic 1, this guy also stays at logic 1 and the motor keeps running up until somebody presses the stop push button. Because now when you press the stop push button here, as I end, when you press the stop push button, what happens is the contact here, remember it was shaded, meaning it was allowing logic to pass through. Now, because you've pressed the stop push button, it breaks that path. So because the path is broken, of course, this goes to logic 0. We'll have a logic 0 here because now we have a logic 0 here. So it's not allowing anything to pass through, and so we have a logic 0. And the moment this guy takes a logic 0, this guy has to take a logic 0, and so the motor will stop running. Okay, remember the overload is just an inbuilt system to protect the motor. So that is how we design our ladder diagrams. I have overshot your time by 2 minutes. I am sorry, but I needed to explain this. Please read this again. We'll do more examples like this to illustrate exactly how we draw ladder diagrams. This one is already drawn. We just needed to explain and see how it works. So unless there's a question, please allow me to stop my discussion for today because time is up and I have another class. So I'll stop sharing and ask if there is any quick question. If there is none, then we'll end the class here. Let me just check the chat. Usually I find that students have put some comments in the chat and I didn't see. So today I see no, I don't see any comments. All right. I think we'll end here. Thank you so much for listening. Please read your notes because from next week we are going deep into the PLC programming and we'll be writing